Now we start chapter 6, module 6. In this module, we shall see how Fourier sine transform and Fourier cosine transform can be applied to solve linear ordinary differential equations. If a differential equation, ordinary differential equation, is defined in a semi-infinite interval, that is in the interval 0 to infinity, then to solve this differential equation, one has to use either Fourier sine transform or Fourier cosine transform depending on the type of boundary condition specified at x equal to 0. If the dependent variable of the differential equation, that is y, at 0 is prescribed, then Fourier sine transform has to be used, while if dy dx at x equal to 0, that is y dash 0 is prescribed, then one has to use Fourier cosine transform. This will be clear from the following examples. Example 1, solve the ODE d2f dx2 minus f equal to e to the power minus x, x lying in the interval 0 to infinity. Given that f at x equal to 0 is 0 and f x tends to 0 and also f dash x tends to 0 as x tends to infinity. Now, since f at x equal to 0 is prescribed, so we shall use sine transform. Why we shall use sine transform? This will be clear shortly. Now, we will multiply the given differential equation by root over 2 by pi into sine Sx and will integrate with respect to x from 0 to infinity to obtain root over 2 by pi integral 0 to infinity d2f dx2 minus f into sine Sx dx equal to root over 2 by pi 0 to infinity e to the power minus x sine Sx dx. That means, we have taken the Fourier sine transform for the given differential equation. Now, we calculate the term separately. First, we calculate the integral from 0 to infinity d2f dx2 sine Sx dx, and we integrate by parts to obtain f dash x sine Sx, x from 0 to infinity minus s integral from 0 to infinity f dash x cos Sx dx. Now, we have assumed that, or it is given that f dash x tends to 0 as x tends to infinity, so that this term at as x tends to infinity becomes 0, and at x equal to 0 sine Sx is 0. So, the first term vanishes. So, we are left with only the second term, that is this integral, and this integral is again integrated by parts to obtain minus s into fx cos Sx x from 0 to infinity plus s integral 0 to infinity fx sine Sx dx. Since from the given condition fx tends to 0 as x tends to infinity, so from this term as x tends to infinity, this term tends to 0, and now f at x equal to 0 is 0, it is given. So, for x equal to 0, f 0 is 0. So, this first term is 0 and we are left with the second term, and this is the second term is this integral is the Fourier sine transform of small f x multiplied by root over pi by 2. So, this integral on the left hand side becomes equal to minus root over pi by 2 s square capital F s s, which is the sine transform of small f x. And this sine transform of small f x, that is capital F s s, is defined as root over 2 by pi integral 0 to infinity f x sine s x dx s positive. So, calculating each term of this step, we obtain this expression reduces to minus s square capital F s s minus f s s, that is equal to root over 2 by pi s divided by 1 plus s square. Simplifying this, we get capital F s, I am stating capital F s instead of capital F s s every time. So, capital F s is equal to minus root over 2 by pi s by 1 plus s square whole square. Now, if I can find the inverse sine transform of right hand side, then inverse sine transform of left hand side will give the function, unknown function f x, and we obtain the solution of the given differential equation. So, the problem now boils down to finding the inverse of right hand side of this equation. So, we get small f x equal to root over 2 by pi minus Fourier sine inversion of s by 1 plus s square whole square. Now, we write the expression s by 1 plus s square whole square as, that means we break this expression to obtain f x as minus root over pi by 2 capital F s inverse of root over 2 by pi 1 by s square into root over 2 by pi s by 1 plus s square, and that is equal to, if we take the Fourier sine inverse knowing the definition, this gives minus integral 0 to infinity root over 2 by pi 1 by 1 plus s square into root over 2 by pi s by 1 plus s square into sine s x dx. If we call this integral as capital G and this integral as capital H, then we obtain f x equal to minus integral 0 to infinity capital G s into capital H s sine s x dx, where capital G is root over 2 by pi 1 by 1 plus s square and capital H is root over 2 by pi s by 1 plus s square. Now, we know that capital G is the Fourier sine transform of the function e to the power minus x. So, that small g, which is the Fourier inversion of capital G, that is equal to e to the power minus x. Now, we consider the integral, this integral, that is 0 to infinity integral g s capital H s sine s x ds. Capital G, as we know, it is the Fourier cosine transform of small g u, and we, instead of capital G, C, we write the Fourier cosine transform of small g, so that we get this integral as root over 2 by pi integral 0 to infinity into e to the power 0 to infinity g u cos s u du into h s sin x s ds. Now, we interchange the integrals. In this step, u integral was the inner integral, s integral was the outer integral. Now, we interchange the integration. So, we now get the outer integral as u integral and inner integral as s integral. So, that this step gives equal to half integral 0 to infinity g u into root over 2 by pi integral 0 to infinity h s sin s u plus x ds plus root over 2 by pi 0 to infinity capital H s sin s mod of x minus u ds. Now, from this step we get this step by interchanging the order of integration and also considering the formula for sin x s and cos s u. So, that we get sin s u plus x and sin s mod of x minus u. Now, this become equals to, this integral becomes equals to half of integral 0 to infinity g u small h x plus u du. This first term stands for this, where capital H is the Fourier sine transform of small h. So, we get the first term, and the second integral here, this range of integration we will break into 0 to x and x to u. So, that the whole step becomes half integral 0 to infinity g u h x plus u du plus half integral 0 to x g u root over 2 by pi 0 to infinity capital H sin x minus u ds minus half x to infinity g u root over 2 by pi 0 to infinity capital H sin s u minus x ds. So, that means here in this integral, second integral, if we break the u integral into 0 to x and x to infinity, then in the first integral x is greater than u and in the second integral x is less than u. So, that mod function reduces to the corresponding values, and this can be again simplified to get half of integral 0 to infinity g u small h x plus u du plus half 0 to x g u small h x minus u du plus half x to infinity g u small h u minus x du, because h x minus u comes from this term. Capital H is the Fourier sine transform of small h. So, we get for this term we get small h x minus u, and for this term we get small h u minus x. So, that finally we get half of integral 0 to infinity e to the power minus u e to the power minus x plus u. We substitute the values of g and h plus 0 to x e to the power minus u e to the power u minus x minus integral x to infinity e to the power minus u e to the power minus u plus x, and that can be simplified finally to get x by 2 e to the power minus x. Hence, f x is given by minus x by 2 e to the power minus x. We may note here that in the sign inversion formula, small h x equal to root over 2 by pi 0 to infinity capital H x sin s x dx, here x is always positive. So, in example 1, we have used Fourier sine transform since f at x equal to 0 is given. Now, we shall consider another example. In example 2, we are to solve the ordinary differential equation given by d2f dx2 minus k square f equal to minus 1 when x lies in the interval 0 to 1 and 0 when x lies in the interval 1 to infinity. Here k is a positive constant and the condition given is f dash at x equal to 0 is 0. Also, f x and f dash x tends to 0 as x tends to infinity. In this case, we shall apply Fourier cosine transform. To apply Fourier cosine transform, we multiply both sides of the given differential equation by root over 2 by pi cos s x dx and integrate with respect to x from 0 to infinity. In the right hand side, since x is non-zero between 0 to 1, so the integral here is from 0 to 1. Now, we simplify various terms. First of all, we simplify the term integral 0 to infinity d2f dx2 cos sx dx. We integrate by parts, which gives f dash x into cos sx x equal to 0 and infinity plus s integral 0 to infinity f dash x sin sx dx. Now, the boundary condition given is that f dash x tends to 0 as x tends to infinity. So, the first term here becomes 0 as x tends to infinity. At x equal to 0, cos sx is 1. So, we need to know f dash at x equal to 0. Since f dash at x equal to 0 is 0 given, so using that this whole term becomes 0. So, for using cosine transform, f dash at x equal to 0 has to be prescribed, otherwise this cosine transform cannot be applied. So, since first term becomes 0, so this integral becomes equal to s into integral from 0 to infinity f dash x sin sx dx. This is integrated by parts to obtain s into f x sin sx x equal to 0 and infinity minus s integral 0 to infinity f x cos sx dx. Now, from the condition given, f x tends to 0 as x tends to infinity and sin sx is equal to 0 as x equal to 0. So, this term vanishes and we are left with minus s square 0 to infinity f x cos sx dx. and this is equal to minus root over pi by 2 s square Fourier cosine transform of small f x, that is capital F C S. And capital F C S is defined as root over 2 by pi integral 0 to infinity small f x cos s x dx. Thus, with this simplification, the given differential equation after taking Fourier cosine transform reduces to minus s square capital F C S minus k square capital F C S equal to minus root over 2 by pi sin s by s. So, that F C S equal to sin s by s into 1 by s square plus k square. Now, to obtain small f x, that is the solution of given differential equation, we have to take the inverse Fourier cosine transform of this equation. So, that taking inverse Fourier cosine transform of the left hand side gives small f x, that is equal to Fourier cosine inverse of root over 2 by pi sin s by s into root over 2 by pi k by s square plus k square into root over pi by 2 into 1 by k, and that is equal to root over pi by 2 1 by k Fourier cosine inverse of G s capital G s and capital H s, where capital G s is the function root over 2 by pi sin s by s, and we know that this is the Fourier cosine transform of the function small g x equal to minus 1 for x lying between 0 to 1 and 0 otherwise, and capital H s is the other function root over 2 by pi k by s square plus k square. So, that small h x, which is the Fourier inversion of capital H s, is equal to e to the power minus k x for k positive. Thus, with this knowledge, we find small f x, which is the solution of the given differential equation, as root over pi by 2 1 by k root over 2 by pi 0 to infinity integral capital G s capital H s cos s x ds, and that is equal to 1 by k integral from 0 to infinity root over 2 by pi integral 0 to infinity g u cos s u du. This term we have written in place of capital G s, and that multiplied by capital H s cos s x ds. Now, we interchange the order of integration. That means, in this step u integral was the inner integral, s integral was the outer integral. In the next step, we will interchange the order of integration, so that u integral will be the outer integral and s integral will be the inner integral, and also the term cos s u into cos s x, that will be written as half of cos s u plus x minus cos s u minus x. So, that f x becomes equal to 1 by 2 k integral 0 to infinity g u into root over 2 by pi 0 to infinity integral capital H s cos s u plus x minus cos s u minus x ds du. Now, H s is the Fourier transform of small h x. So, here this integral, first integral, this becomes equal to h of u plus x, and the second integral will give small h of u minus x. So, that we get f(x) equal to 1 by 2k integral from 0 to infinity g u into small h of u plus x minus small h of mod u minus x du. So that this is equal to, knowing small g u and small h u, this is equal to minus 1 by 2k 0 to 1 integral e to the power minus k u plus x minus e to the power minus k mod of u minus x. Now, the u integral is from 0 to 1. For x lying in the interval 0 to 1, f(x) is equal to, we get from the previous step that is equal to minus 1 by 2k integral from 0 to 1 e to the power minus k u plus x, which comes from the first term, minus, we break this, for this integral we break the integral from 0 to 1 as 0 to x and x to 1 to get minus integral 0 to x e to the power minus k x minus u du minus integral x to 1 e to the power minus k u minus x du, and that is equal to minus 1 by 2k. We take out e to the power minus kx integral from 0 to 1 e to the power minus ku du minus e to the power minus kx 0 to x e to the power ku du minus e to the power kx integral from x to 1 e to the power minus ku du. This can be simplified and manipulated to get finally f(x) equal to 1 by k square 1 minus cos hyperbolic kx minus e to the power minus k cos hyperbolic kx, which is simplified again to obtain f(x) as equal to 1 minus 1 plus e to the power minus k cos hyperbolic kx by k square, and that gives the solution for the given differential equation when x is between 0 and 1. Now, for x greater than 1, we write f(x) from here as f(x) equal to minus 1 by 2k integral 0 to 1 e to the power minus k u plus x du minus 0 to 1 e to the power minus k x minus u. Here x is always greater than u. So, this integration can be performed to give minus 1 by 2k square e to the power minus kx into 1 minus e to the power minus k minus e to the power minus kx into 1 minus e to the power x, and that can be simplified to get minus 1 by 2k square e to the power minus kx sin hyperbolic k, and that gives the solution of the differential equation when x is greater than 1. So, in this module we have learned how to use Fourier sine transform or Fourier cosine transform to solve ordinary differential equation, and we have also learned when to use Fourier sine transform and when to use Fourier cosine transform. With this we conclude module 6 of chapter 6.